Welcome back, Mac 1330 Fluid Power. We are getting into Chapter 12 with Pneumatic Components. All right, so, where are we going to use pneumatics? Lots of air tools. All right, so you can see a lot of pictures there. All right, putting torque, tires, things like that. Pneumatic cylinders. Okay, same basic construction and configuration as hydraulic cylinders. So a lot of stuff in this chapter. We're going to be doing some duplicate stuff that we did with hydraulics. So I might brush through that real quick. Now, since they operate at much lower pressure, they are of much lighter construction. All right, so not quite as heavy duty on the pneumatic cylinders as we are with the hydraulic cylinders. However, they are quicker acting and they are less precise. We are still using Pascal's law, all right, for extending and retracting a cylinder. All right, so our extending force is still pressure times area. All right, so when we're extending, it's just pressure times the area of the piston. When we are retracting, okay, the F sub R is retracting. It's pressure times the difference in the air. Remember the rod end, the volume's different on that side. We take care of our pressure in gauge pressure, all right? And gauge pressure is the pressure above atmospheric pressure, so remember that, okay? So let's take a look. We got a double-acting pneumatic cylinder. Has a 3-inch bore, 1.5-inch rod is to be used in the system with a supply of 100 psi gauge. What's the output force of the cylinder on the extend and retract? Okay, we did a million of these in earlier chapters with hydraulics. Same thing, for the most part, although we just have to do some other pressure calculations, all right? So first thing is first, right? We still have to find the area of the piston, the area of the rod. That hasn't changed. It's pi d squared over 4. The biggest thing here is when we do the extension force, okay, it's going to be pressure times area of the piston, okay, when we do this. If we want the retraction force, all right, it's pressure times the difference in the area, so you get 529 pounds, okay? So very simple. That's all repetitive stuff we've done. Nothing super new here, other than we're adding, using the stroke length. Okay, so we have the extension velocity is going to be the area of the piston times the stroke, or the velocity of the retraction is going to be the difference in the area times the stroke. Okay, and then the slide, you can see pictured there. It's a cylinder with guide rods, that run parallel to the piston. You can see that in class on our 870 trainer station 1. All right, our pickup cylinder has guide rods on it. Okay, so let's do an example here. A double-acting pneumatic cylinder with a 3-inch bore and a 1.5-inch rod and a 5-inch stroke length must cycle. That means extending and retracting 40 times per minute. So the supply pressure is 100 psi gauge. What is the air consumption? All right, so this is going to deal with the equations on the previous slide. First steps, same as what we've been doing all semester. Calculate the area, pi d squared over 4. Then we have to calculate our extension, okay? Area of the piston times our stroke length, okay? And then the difference in the area times the stroke length. And then get our total by combining them, because that's our full extension and retraction, okay? So when we calculate, that's the total volume per cycle, okay? Then we have to convert to cubic feet, okay? Because we're in cubic inches. Okay, and then we want to calculate the uncompressed volume, since we want to require it at 100 psi gauge. Okay, so notice what we have to add here is atmospheric pressure, all right, because we're using absolute pressure. So we're going to take 100 plus 14.7, and we're going to take 0 plus 14.7. Our first pressure, our initial pressure, right, when we start is at 0. So that's why we're doing 0 plus 14.7 for this. Okay, so that's our volume on that. Pneumatic motors, all right, they're similar in function and construction to hydraulic motors. We use them where there's low to moderate torque that's required. We can operate at speeds in excess of 10,000 RPM, and our hydraulic motors are limited to 5,000 RPM. So a lot more speed, but with speed, right, speed and torque are inverses of one another, so we're going to get less torque in this scenario. But you'll run some labs with the pneumatic motors as well. Okay. Now, the advantage is they can stall under full load for indefinite periods of time. They can be used where electric motors are considered to be a fire hazard. So that's a lot more important there, right? Because there's no arcing or sparking or anything along those lines. And they're lighter and less expensive than electric motors. All right, some of the basics, okay, we're going to talk about is their running torque. That's the torque generated when the motor is operating at a particular speed. We're going to look at their starting torque. That's the torque generated when a motor is started from a dead stop. Their stall torque. That's the torque required to stop a rotating motor at a particular supply pressure. All right, it's always higher than the starting torque because it must overcome the momentum of the motor. Remember, speed will depend on the load and the supply pressure. If the load is increased, the torque will likely increase, meaning speed will decrease. Okay, just like everything that we did in mechanical, speed and torque are inverses of each other. If the supply pressure is increased, then the speed will increase, and if that increases, all right, our torque will decrease. But if the supply pressure decreases, then our speed will also decrease, all right, increasing our torque. So some different terminology with pneumatic motors. All right, we have the free speed. That's the speed under no load at a particular pressure. We have the design speed, the rotational speed at the maximum power output. All right, so if we take a look at the schematic symbols here, notice our pneumatic motors have the same symbol as we did with the hydraulic motors, only the triangles are now empty, showing pneumatic. Remember, if they were hydraulic, the little triangles on the circles here would be filled in, all right, indicating that they are hydraulic. So when there is one triangle, it's a unidirectional motor, meaning it can only go forward or it can only go backwards, all right, or clockwise or counterclockwise as we deem them. Or we have a bidirectional motor, okay? It can also go clockwise or counterclockwise. We have grippers, all right? We use those to pick up and manipulate parts. We have grippers on the end of all of our robots except for one. We have escapements. Okay, that allows parts to be released one at a time. All right, and we have some of that on the 870 trainer on station 4, all right, as it waits in queue to be processed by the robot. Same with what we did with hydraulics, all right, directional control valves or DCVs. Okay, so we have 2 ways, 3 ways, or 4 ways. And then same with positions. Positions are based on the number of blocks that you see on the schematic. Okay, so the first one shown here is a 2-way, 2-position, okay, and this is a normally closed valve, all right, nothing's allowed to flow there. Okay, if you have a 3-way, remember ways are, we're going to look at the letters on the outside of it, usually P, T, and A, and so on and so forth, or we throw a B if there's a 4-way, okay, but that's going to tell us, you know, if we are normally opened, normally closed, all right, but we still have the same thing. So the bottom one, okay, is a 3-way, 2-position DCV. We can also have the 4 ways, all right, like we talked about. This is all very similar to hydraulics, so I'm not going to spend a lot of time going through this, all right, but, you know, notice on this one, it's a 4-way, 2-position directional control valve on this schematic. And then remember, hydraulics used a detent, sorry about that, a mechanism holding it in place for the positions. Pneumatics don't. They use low pressures and tight seals that allow them to maintain position. Okay, same kind of way if we are extending or retracting. All right, so for us to retract, we're putting air into the rod end and evacuating it out of the port end. Okay, or vice versa. If we are extending it, we're putting air into the blind end. All right, and evacuating it out of the rod end. Okay, and remember with pneumatics, we can vent to the atmosphere. These are all the same symbols, so we should be much more successful on the test here. All right, making sure that we understand what a manual lever looks like, a push button, a foot pedal, a cam, a pilot operated valve, a solenoid, or a pilot operated solenoid. Okay, we spent a lot of time talking about those in hydraulics. We also have check valves, okay, just like we did in hydraulics, shuttle valves, okay, same thing, and then and valves. So a little bit differently, right? And valves require pressure at P1 and P2 simultaneously for flow to be sent to the outlet. So this and this have to happen, and then we send it out. You know, like examples at like Fast food restaurant where you want to get Coke from the soda dispenser. All right, when you push the arm back, all right, it's probably a limit switch or something back there, that clicks, puts that back, and it sends the syrup and the carbonated water at the same time and mixes right before it goes into your cup. So example of where you might use an AND valve. I know that's not necessarily pneumatics, but still fluid power. All right, so lots of logic valves, and we can use those all in areas where electrical control presents a fire hazard. All right, we're trying to eliminate any sparking or arcing that's created by electricity that could start fires. Okay, we have a quick exhaust valve. We use that to increase the speed by speeding up the exhaust flow. Okay, flow coefficient, same thing that we talked about with hydraulics, only in this case we're going to bring temperature into the realm here. Okay, so T is temperature. So we're either going to be in Rankine if we're talking imperial or our standard units here, or we're going to be in Kelvin if we are in metric. Okay, delta P hasn't changed. All right, our flow coefficient, that's a sizing tool for us. A value with a large flow coefficient will have a smaller pressure drop across the valve for particular flow rates. Okay, our critical pressure ratio is always output over input. All right, decreasing that ratio and no further increase in flow, and the valve becomes choked. All right, so let's do a couple examples real quick. We want to find the flow coefficient. An air-powered machine consumes 25 standard cubic feet per minute at 90 psi gauge. If the directional control valve that will control this machine can have a pressure drop of no more than 5 psi, what is the minimum flow coefficient? Okay, assuming the temperature of air is 80 Fahrenheit. All right, so first and foremost, make sure that we get everything into the correct units that we want to. So our output pressure, we're going to have to take 90 plus atmospheric pressure, so 90 plus 14.7, and get 104.7 for our absolute pressure. And we have to take 80 plus 460 because we got to go Fahrenheit to Rankine to do our calculation. Next, substitute all of our given values into the equation, okay? And we get our flow coefficient of 1.13. Remember, it's going to be unitless, all right, with that. So if we choose a value of 1.13 or higher, ensures that the pressure drop will not be more than 5 psi. So that's why we want to use, a flow coefficient, all right, as a gauging tool for us. If we want to do the same problem in metric, all right, we have an air-powered machine that consumes 750 liters per minute at 650 kPa gauge. If the directional control valve that will control this machine can have a pressure drop of no more than 40 kPa, what is the minimum flow coefficient, assuming temperature of air is 30 Celsius? Just like the previous one, we got to make sure we put everything into the correct units. So our output pressure has to be 650 plus 101. All right, that's atmospheric pressure for metric, and then we have to make sure we're in Kelvin, so we got to take 30 plus 273 to get our temperature in Kelvin. Then we substitute in our given values, all right, and we get 1.09 for our flow coefficient, okay? So that means if we choose a value of 1.09 or higher, the pressure drop will not be more than 40 kPa in the system, okay? Now let's say I give you the flow coefficient. We want to find the flow itself, all right? A valve with a flow coefficient of 1.25 is used in the system with a line pressure of 100 psi gauge. The pressure drop across the valve is 10 psi. What's the flow through this valve if we're assuming the temperature is going to be 80 degrees Fahrenheit? Okay, so we have to convert all of our absolute values. So outlet pressure is going to be 100 minus 10 because we have a pressure drop of 10 psi. Okay, so the line, right, is reading 100 psi gauge, but we have a pressure drop of 10, so we have to do 100 minus 10 first and use 90, and then add 90 to 14.7 to get our absolute psi of 104.7. Okay, then we have to take 80 plus 460 so that we are in Rankine for this problem. Then we have to solve the equation for Q, okay? We're using flow rate now and not flow coefficient. All right, so once we've solved it for Q, we substitute all of our given values, and we get our flow as 39.1 standard cubic feet per minute. So a larger pressure drop will have a higher flow rate when we talk about those, okay? Now, how do we put them right? Pneumatic flow control values, with a return, values with a return check, all right, for I cannot speak today, flow in the reverse direction. Flow will be controlled from A to B, but B to A is unrestricted. Remember, that's a check valve, right? Remember, we're only allowing flow in one direction for that. Okay, we also use them to connect in a meter in or meter out. If you remember, we talked about that in hydraulics. The most common one is we want to meter out, okay, whether we either want to slow down that extension or retraction. So metering out is the most common. Remember, we can use them as a manual shutoff valve as well, but we can meter either how much air is flowing into the system, right, to extend or retract, or how much air is flowing out of the system to extend or retract. So that was our meter in, meter out. Very, similar to what we talked about with hydraulics. Okay, pressure relief valves. Okay, and you'll notice these are all the same, so I'm not spending a bunch of time on everything here. Pressure relief valves. Okay, spring-loaded valves that open when a preset maximum pressure is reached to prevent further rise in pressure. Pressure regulators, all right, we use those to supply pressure to the appropriate level for a particular machine. All right, we have those pressure regulator pretty much on every single pneumatic system that we have here in the lab. Filters, we use the filters to remove contaminants from the air. They can cause damage to components. All right, we don't want particles and things like that get inside the lines and bounce around and do damage. And, normally we get small chunks of rust or things like that because we're in a conduit and there's moisture inside there. And that moisture, eats away at the metal on the inside. We have lubricators that are built into the system. Okay, it's a fine mist oil that's sprayed into the airflow. Just like we talked about with like our pneumatic nailer in class and things like that. A couple drops of fluid in, and then we allow the air to flow through the system and lubricate everything. Okay, and then we have our combined conditioning units. Okay, we have a filter, a regulator, and a lubricator combined into one unit called an FLR or an FRL. You can see that pictured here down below. We also have these on the 870 trainer. So we use our pressure regulator to allow a certain amount of pressure into that particular system, whether it's station 1 all the way up to station 7. Okay, and then we also have that filter that's in the line to catch any water or any other contaminants that might be going through. Okay, so we have to be able to remove those water particles. Okay, so in pneumatics, water exists as water vapor, okay, and as a liquid water. So when it is in liquid form, it becomes problematic because it can cause corrosion and reduction of effectiveness, right? That corrosion with air, right, produce rust. We chip on the inside, get those particles inside. So we always kind of pay attention to what the relative humidity is. That's the percentage of water in the air as combined to the maximum amount can hold. So sometimes on, TV or you're watching the news, they talk about relative humidity, and when the humidity's up, that's the percentage of water that's actually in the air. That's why it feels very humid when we go outside in the summer. All right, we have the dew point. That's the temperature where the air becomes saturated with water. Okay, we put air dryers in the system to help reduce water in the air. We have refrigeration dryers. Okay, we use a refrigerant that is compressed and heated and then expanded and cooled. We also have absorption dryers. Okay, we use a gel material that absorbs water as the air is passed through it. They're used to drop to the dew point. Okay, so for the most part, when we use pneumatics, we generally have a centrally located compressor and receiver tank, right? We talked about those in the last chapter. All right, and we distribute it through the facility through a distribution header, kind of like the ones shown below. We don't have one exactly like that, but if we went to Nissan and looked at the line and a bunch of people that were tapping into the main line, we would have all these different taps on the main line. Okay, so we drop a line and it supplies it at that specific machine. So, if you look over in class, we have some supplying the robots, all right, and we're going to have some supplying the 870 trainer, some are supplying the plasma table and things like that. Usually, for the most part, you use Schedule 40 steel pipe, or we call it conduit, all right, and it's just like in our lab. So I'll walk over and show you guys what that looks like in our lab. So, guys, that's it for Chapter 11. We got one more chapter to go for pneumatics, and we are done for the semester. So, as usual, email me with any questions or ask when you get to lab. Else, have a great day, and I'll see you in class.